So one of the things have to be able to do in this chapter is calculate the percent mass of a compound from its chemical formula, and also to be able to use that number in calculations like conversion type calculations. So let me show you how you do that. Um, Here's the formula for iron oxide, iron 3 oxide, which is rust, right? So what we're going to do is we're going to calculate the mass percent of iron, Fe2O3, um, from its chemical formula. So part of what we'll need for this, we'll need to know the atomic masses for iron and oxygen. So we haven't looked at iron very much, so let's go ahead and pull iron up. Iron is here, it's 55.85. So 55.85, and we'll drop back into here. So I know Fe is 55.85 atomic mass units, and then we know oxygen as being 16.00 atomic mass units. Now, when I say calculate the mass percent of iron in iron oxide, what I'll need to do is treat the iron as the part and treat the Fe2O3 as the whole. Okay, so we know to calculate a percent, it's part over whole times 100. So the part, since there's two irons in here, and I'm going to write it out like this, although you could calculate them out separately and then write them in, it's going to be 2 times the 55.85 at the top, and these are all in atomic mass units. And at the bottom, it's going to be 2 times 55.85 plus 3 times 16.00. So this is the part, this is everything, right? And then we just multiply it by 100 to get percent. So I'll pull up my calculator for that. And maybe what I'll do is I'll write the parts out. So 55.85 times 2, that's going to be 100. Let's go back to this format. It's easy. 111.7 atomic mass units, and then at the bottom I'm going to add the 55.85 to the 3 times 16, so I'm just going to say plus 3 times 16, and that's 159.7, and then times 100. So let's go ahead and throw that in the calculator, and we're going to go 111.7 divided by 159.7. And that's going to be equal to, and then I just move the decimal twice, or I'll hit times 100, and I'll get 69.94. Now this should have 4 significant figures. I'll carry one more because I'm going to use this in calculation. So 69.94, and I'll round that 3 to a 4 like that. And this is in percent units. Oops, sorry. Just kind of shifted pages by accident. Percent. Now, how could you use that? Well, it turns out this mass percent, it doesn't involve any units. So I can use the percentage by mass to convert any mass unit over. For example, how much rust will 1.23 kilograms of iron produce, right? So how much Fe 2O3 could I get from 1.23 kilograms of iron? Like that. And then I know the mass percent is 69.944. What does that mean, right? It means, for example, 69.944 grams for every 100 grams. For example, that's the idea of percent. But the grams on the top is the grams of iron, and the grams on the bottom is the Fe2O3. That's the mass percent of iron in grams for 100 grams of rust. But I could just as easily write this. So we're going to do it as kilograms for every 100 kilograms of Fe2O3. So either one of those can be written. They basically mean the same. It's the per 100 parts. So it doesn't matter whether you write it as kilograms or grams, or you could do it as pounds. And actually, the pounds one is an interesting one because when we do fertilizers, we want to know how many pounds of nitrogen we're applying to a field, for example. In order to do that, you take the mass percent of nitrogen, which then you multiply that times the pounds of fertilizer, and that tells you how many pounds of nitrogen are coming out, for example. Okay, so this kind of calculation gets used a lot in different ways. Okay, so let's just use it on this iron, and then we're going to do one with my car. Anyways, so I can write, this is kilograms of iron. So then the iron has to go on the bottom. So it's 69.944. Now 3 sig figs, or 4 sig figs, kilograms of iron. So I can get the units to cancel, right? And this is for every 100 kilograms of Fe2O3. So I can pull my calculator out. I can say 1.23 times 100 divided by 69.944, and I'll end up with one. Oh, I think I screwed up a number in here. 100. Oh yeah, I said 1023. Let me redo that. It's 1.23 times 100 divided by 69.944. Yeah, it looks like a more reasonable answer. That's 1.7585 kilograms of iron oxide, rust, right? With 3 sig figs, because it's 1.23, so 3 sig figs, and so that'll come out to be 1.76 kilograms of Fe2O3, like that. And that would be your answer. We'll do another one. I guess this is just kind of a funny one on my part. How many pounds of rust could be produced from my 66 Ford Mustang? It's curb weight, and assume it's all iron, of 2,445 pounds. So this would be the equivalent of nitrogen, for example. But if that's how much my car weighs, how much rust could I make out of it, assuming it's all iron? And, there's a few bits, piece of vinyl and stuff like that in there. So we're going to go like this. We're going to say, we're going to look for pounds, right, of Fe2O3. You could have just said pounds if you wanted to. And then you have 2,445 pounds times, or railroad tracks, and then the same mass percent composition that we used up here. So it's going to be, oh, sorry, this is pounds of iron. Let me just redo that. So I have 69.944 kilograms, or pounds, sorry. The gnats have come out. For every 100 pounds of Fe2O3, like this. This is pounds of iron at the bottom. So we'll get this to cancel out like this, right? And be left with these units here. So again, same kind of thing. You pull out your calculator at this point, and you'll just say, let's see, 2,445 times 100, and then divided by 69.944. So regardless of how you're using this number, like what you're using it to convert, it's always the same number for the mass percent composition of iron and iron oxide. So that comes out to be a lot of rust, 3,495.65 pounds of Fe2O3. Let me double check that I got that number right. 3,495.65 pounds. Now there's only 4 significant figures in that, so that would be 3,496 pounds. That's a big pile of rust. And we're heading in that direction anyways, so we got to stop that somehow. Okay, so this is one I want you to do. Okay, it says how many grams of oxygen are found in 125 grams of ethyl alcohol. So I'll get you started, and then I'll let you guys finish the calculation. We'll pause it, and then I'll come back with the solution. So again, you need to find the mass percent. This is the formula for ethanol. You need to find the mass percent of oxygen in ethanol. This is how we're going to do this problem. And actually, I'll be showing you in the next few chapters other ways you could actually do this problem. But for now, we're going to go ahead and do it as a mass percent problem. I'll be starting with 125 grams of ethyl alcohol, and what I want to do is figure out grams of oxygen. So the first thing I need to do is figure out the mass percent, which is going to be the oxygen, right? Mass of oxygen. Let me write it over here. Mass of oxygen, and we'll do it in atomic mass units. It doesn't matter what kind of unit you use, really, but as long as you're consistent. And at the bottom, we're going to do the mass of ethyl alcohol. So that's I'll simplify it, C2H6O, like that. So I just condensed the formula times 100. Okay, so that's what you'll have to do, and then you'll use that number to convert to grams of oxygen. So go ahead, like even if you're not sure what to do, at least calculate the mass percent of oxygen. Just base it off of the mass percent of iron in iron oxide. Okay, we'll pause there, come back with the solutions. Let's walk through the rest of this problem. Here's where I calculated the molar mass, or the mass of the molecule of ethanol. So this is 2 carbons, 6 hydrogens, and 1 oxygen, come out to be 46.068. Now, knowing that, then what I can do is calculate the mass percent of oxygen in that formula by saying 16, because there's only 1 oxygen in there, right? Divided by the mass that I calculated over here times 100, and that gives me 34.731%. Now, anytime you do one of these calculations, just track the sig figs, right? So this is going to have 4 sig figs. I went ahead and carried 1 or 2 more digits usually, so I don't have any rounding problems later. And then what I'll do is I say, okay, well, I have 125 grams of C2H6O, and this percent is the same as saying 34.731 grams of oxygen for every 100 grams of, this is ethyl alcohol, ethanol. Same stuff they make out of corn and they put in your gasoline, right? So, and then you have 43.41 when you do this calculation, divided by, 125 times the 34.731 divided by 100, you end up with 43.41 grams of oxygen, which with 3 sig figs, because of the 125, right, 3 sig figs, then this comes out to 43.4 grams of oxygen. So that's actually the oxygen content. One of the things they do when they calculate additives for fuel is they want to know how much oxygen it actually brings to the chemical reaction. So that's the grams of oxygen you would get out of 125 grams of ethyl alcohol.